Greetings, students, and welcome to today's exploration of an intriguing challenge from LeetCode, specifically Problem 242. This problem invites us to delve into the fascinating world of string manipulation by determining whether two given strings are anagrams of one another. An anagram occurs when two strings can be rearranged to form each other, utilizing the same characters in identical frequencies, regardless of case. For instance, consider the strings listen and silent. Despite their differing arrangements, they share the same letters, L, I, S, T, E, and N. As such, they are classified as anagrams, and the expected output for this pair would be a resounding true. As we dissect this problem further, we will employ various methods to ascertain the relationships between characters in these strings. Let us embark on this intellectual journey together. A frequency array with a list is a powerful tool for counting and storing occurrences of elements in a dataset. Think of it like a scoreboard that tracks how many times each player scores in a game. In this case, the score corresponds to the occurrence of an element. When we create a frequency array, we initialize an array where each index represents a unique element, such as an integer. The value at each index shows how many times that integer appears. For example, if our dataset includes the numbers 1, 2, and 2, the frequency array would tell us that 1 appears once and 2 appears twice. This structure is especially useful for quickly assessing how elements are distributed, which enhances performance in algorithms like counting sort. By iterating through the dataset and updating our frequency array, we achieve a clear and efficient way to manage counts, often in linear time. This approach not only streamlines data analysis, but also optimizes searches based on frequency, making it a fundamental concept in programming and data science. In this example, we're creating a function called frequency array that counts how often each element appears in a list. The first step initializes an empty dictionary, freqdict, to store each unique item and its corresponding count. As we go through each item in the input list, we check if it already exists in our dictionary. If it does, we simply increment its count. If it doesn't, we add it to the dictionary with a count of 1. Once we have counted all the occurrences, the next step involves creating a frequency list. This list will contain the counts of each item in the original order they appeared. We achieve this with a list comprehension that pulls the count from freqdict for each item. Finally, we return the constructed frequency list. For instance, if we input the list apple, banana, orange, banana, banana, the output will show how many times each fruit appears, giving us a clear picture of the frequency of each element. Character-to-index mapping using the ORD function is a key concept in computer science, allowing us to convert characters like A, B, or 3 into their integer representations based on the Unicode standard. In Python, the ORD function takes a single character as input and returns its corresponding integer value. For instance, ORD-A gives us 65, while ORD-A returns 97. This mapping is essential in various fields, such as data processing and cryptography. It enables tasks like encoding messages, sorting characters, or creating hash tables. By converting characters to numbers, we can perform computations and comparisons more efficiently. At its core, the ORD function accesses a predefined table of Unicode values, allowing programmers to carry out arithmetic operations on characters. This capability is vital for implementing algorithms that involve string matching or frequency analysis, making our programs faster and more effective in handling text. Let's explore how to create a character-to-index mapping using the ORD function in Python. This example comes from LeetCode Problem 242, which deals with character indexing. First, we start with an empty dictionary called mapping. This dictionary will hold our character keys and their corresponding index values. The index will represent the position of each character in the alphabet, specifically for lowercase letters from A to Z. Next, we iterate over each character in our input list. For each character, we use the ORD function to get its ASCII value. By subtracting the ASCII value of A, we normalize the index to a range of 0 to 25, where A is 0, B is 1, and so on. Finally, we return the completed mapping. For example, with the input list of A, B, C, D, our output will be a dictionary showing A0, B1, C2, D3. This method efficiently translates characters into their respective positions, which can be very useful in various programming scenarios. String comparison using the sorted function is a powerful technique that allows us to evaluate the arrangement of characters within strings by sorting them alphabetically. When we apply sorted to a string, it returns a list of its characters organized in ascending order. This transformation standardizes the strings, making it easier to compare their contents based on character order. For example, if we want to check if two words are anagrams, like listen and silent, we can sort both strings and compare the results. If they match, we know they contain the same letters, just arranged differently. Using sorted involves iterating through each character in the string, applying a sorting algorithm, and constructing a new list. This process typically runs in O(n) log n time, where n is the length of the string. This efficiency makes it a practical choice, simplifying our logic and reducing potential errors in string comparison tasks. Understanding this concept lays the groundwork for tackling more complex string operations down the line. This slide presents a function to compare two strings by sorting their characters. The function compareStrings takes two inputs, str1 and str2. First, we sort both strings using Python's built-in sorted function. This rearranges the letters in both strings in alphabetical order. For example, when we sort listen, we get IL-enst, and for silent, we also get IL-enst. Next, we compare the sorted versions of the strings. If they are identical, the function returns true, indicating that the original strings are anagrams of each other. Anagrams are words that use the same letters in different orders, like listen and silent. In the example provided, calling compareStrings listen silent will yield true, confirming they are indeed anagrams. This approach is straightforward and leverages sorting to simplify the comparison process. To solve LeetCode problem 242, titled Valid Anagram, we need to determine if two strings, S and T, are anagrams of each other. An anagram is simply a rearrangement of the letters in a word. First, we check the lengths of the strings. If they differ, we can immediately conclude they aren't anagrams. Next, we initialize a frequency counter, typically a dictionary, to count how many times each character appears in the first string S. As we go through S, we update this count. Then we look at the second string T, and for each character, we decrement the count in our dictionary. If a character in T isn't in S or appears more times than allowed, we know they're not anagrams. Finally, we check if all counts in our dictionary are 0. If they are, S and T are indeed anagrams. This systematic approach ensures we efficiently determine the relationship between the two strings. Today, we will explore a compelling problem from LeetCode, which asks us to determine if a given string, S, is an anagram of another string, T. An anagram is defined as a rearrangement of letters from one word to form another, utilizing each letter precisely once. Key constraints include that both strings will contain only lowercase English letters and will range in length from 1 to 50,000 characters. These constraints significantly influence our approach to designing an efficient solution. The provided Python solution tackles LeetCode problem 242, which asks us to determine if two strings, S and T, are anagrams. An anagram means that we can rearrange the letters of one string to match the other, so both strings must have the same characters in the same quantities. The function isAnagram starts by checking if the two strings are of different lengths. If they are, it immediately returns false, because different lengths mean they can't be anagrams. This check is efficient, operating in constant time, or O1. Next, the algorithm uses a fixed-size frequency array called frequency, with a length of 26, to count how many times each character appears. This is possible because we only deal with lowercase English letters. The array allows us to access counts directly using their character values, making both counting and uncounting operations run in linear time, or ON. In the first loop, we increase the count for each character from string S. Then, in the second loop, we decrease the count for characters in string T. If any count goes below 0, we immediately return false, indicating that T has more of a character than S. Finally, if all counts balance to 0, we return true, confirming that S and T are indeed anagrams. The overall time complexity of this solution is O(n). And since the frequency array size is constant, the space complexity is O(1). This approach is both efficient and elegant, utilizing counting principles effectively in the context of string comparison. Time complexity for LeetCode problem 242 is O(n). This means that as the size of our input strings increases, the time it takes to solve the problem increases linearly. To check if two strings are anagrams, we typically iterate through each character in both strings, counting their occurrences. If the strings are long, we still only go through them once, making this approach efficient. Now, let's talk about space complexity, which is O(1). This indicates that the amount of extra memory we need remains constant, no matter how long the input strings are. We only require a small, fixed amount of space, specifically an array of size 26 if we are only dealing with lowercase letters. This array is used to store counts for each character. So even if we have very long strings, our additional memory requirements don't change. Understanding these complexities is crucial for evaluating how our solutions perform as input sizes grow.